Let us prove by principle of mathematical induction that 2 to the power n is greater than or equal to n square for every integer n greater than or equal to 4. So we just write the statement. Let Pn be the statement 2 to the power n is greater than or equal to n square, n equal to 4, 5, 6, 7 and so on. Therefore, let's initiate it. We will not initiate from n equal to 1 because we are not saying that we don't have to prove it for n equal to 1. We will be initiating for n equal to 4. When n equal to 4, when n equal to 4, comma 2 to the power 4 equal to 16 and 4 square is also equal to 16. Therefore, 2 to the power 4 is greater than or equal to 4 square. Is P4 is true? Yes. Therefore, Pn is true for n equal to 4. Therefore, Pn is true for n equal to 4. So, our statement is true from the starting point n equal to 4. Now, let us do some kind of cycling. Let us assume Pn is true for some n equal to k. So, at the starting point Pn is true. Let us assume Pn is true for some let us assume Pn is true for some fixed n equal to k. Then we want to show that Pk plus 1 is also true. That is, Pn is true for n equal to k plus 1. Then Pk plus 1 is the statement 2 to the power k plus 1 is greater than or equal to k plus 1 whole square. When you take n equal to k plus 1, you have 2 to the power k plus 1 is greater than or equal to k plus 1 whole thing square. Then 2 to the power k plus 1 equal to 2 to the power k into 2. By our assumption, 2 to the power k is greater than or equal to, for that fixed k, 2 to the power k is greater than or equal to k square. Now, we want to show that Pk plus 1 is true. That is, we want two to the power k plus 1 greater than or equal to k plus 1 whole thing square, which is true if a 2 to the power k plus 1 is greater than or equal to 2k square. If 2k square is greater than or equal to k plus 1 whole thing square, we are done. Or if take k square and 2k to the left hand side, you have but for k greater than or equal to 4, comma k square minus 2k equal to k into k minus 2 is greater than or equal to 1. Therefore, Pk plus 1 is true. Therefore, Pk plus 1 is true whenever Pk is true. Now, if we take k equal to 1, we have, we are not starting with n equal to 1, we are starting with n equal to 4. If you take k equal to 4, then this says P5 is true. Then again, if you take k equal to 5, then it says P6 is true. Hence, by principle of mathematical induction, Pn is true for every n.